Imagine standing at the edge of the world, not metaphorically, but literally. Behind you, familiar territory, mapped and understood. Ahead, unknown country, where light itself hasn't reached yet, where the very rules of possibility might be different. You stand where ending and beginning blur together. Hello and welcome to the Sleepy Astronomer. If this is your first journey with me through deep time, welcome to the most speculative exploration we could take together. And if you've travelled with me through the death of the last black hole and the profound silence of the dark era, thank you for staying to this final threshold. Before we venture beyond the known universe tonight, if you're finding wonder in these explorations, I'd be ever so grateful if you'd subscribe to continue these journeys into the unknown. And a gentle like helps fellow wanderers find these contemplations at the edge of physics. Whether you're settling into bed, sitting in darkness, or simply pausing to wonder about ultimate things, I'm honoured you're here. We've completed an extraordinary journey together. In episode 1, we followed a single black hole across 10 to the power of 69 years, from violent birth to gentle dissolution in a final quantum whisper. In episode 2, we contemplated the dark era, that profound silence, the universe settling into near perfect equilibrium, temperatures approaching absolute zero, structures dissolving. We watched entropy approaching its maximum, heat death arriving, not with catastrophe, but with the gentlest fade to stillness. The universe became a place where nothing changes because nothing can change anymore. And we concluded this is the end. But is it? Tonight, we explore what might lie beyond even that ending. These are theories at the bleeding edge of physics, where rigorous mathematics touches profound uncertainty, not wild fantasies, but serious proposals from accomplished physicists, ideas grounded in quantum mechanics, general relativity and thermodynamics, attempting to answer one of the most profound questions we can ask. If the universe reaches heat death, can something come after? We don't have definitive answers. What we have is possibility space, the landscape of what might be, given the laws of physics as we understand them. Some theories have strong mathematical foundations but can't be tested. Others are more speculative but beautifully consistent with what we know. All reveal something important about the nature of reality, time, and existence itself. Think of tonight as visiting several possible futures, several answers to what happens after the end. We'll explore vacuum decay, the possibility that our vacuum might tunnel into a lower energy state that changes the very laws of physics. We'll consider quantum tunneling to baby universes, that space-time itself might bud off offspring, that our heat death might seed infinite other cosmos. We'll examine eternal inflation and the multiverse, inflation continuing forever elsewhere, creating infinite universes, making our heat death just one local event. And we'll contemplate Roger Penrose's radical proposal that our heat death becomes the Big Bang of the next cycle, that time breathes in and out across infinite ages. I want to be clear about what we're doing. We'll be rigorous about what's established, what's speculative, what's testable, and what lies beyond verification. We'll honour the mathematics while translating it into human experience. The boundary between knowledge and mystery is exactly where the most interesting questions live. This episode feels different from our first two journeys. Episode 1 was narrative, a character arc across deep time. Episode 2 was meditative, a contemplation of emptiness. Episode 3 is exploratory, an intellectual adventure into theoretical physics, a map of what might lie beyond the edge of our knowledge. The science gets heavier here, the speculation more explicit. We're venturing where even physicists disagree, where the line between science and philosophy becomes hard to draw. But the wonder remains, that sense of standing at a threshold peering into mystery, feeling the vertigo of not knowing, mixed with the thrill of imagining. Why does this matter? Because these questions touch the deepest issues of existence. Is the universe fundamentally finite or infinite? Is time linear or cyclic? Is our cosmos unique or one of countless others? Does ending even make sense when applied to the universe itself? Can something truly come from nothing? Is heat-death truly final or merely a transition? Humans have always wondered about endings and beginnings. Every culture has creation myths, stories of how something arose from nothing, how order emerged from chaos. The Big Bang gave us a scientific creation story, replacing myth with mathematics while somehow deepening the mystery. Now we're developing scientific theories about what comes after our ending. These are modern creation myths, written in equations rather than poetry, touching the same profound mysteries that have haunted us since we first looked up at stars and asked, why? So let's begin where our last episode ended, at heat death, with entropy at maximum, structure dissolved, the universe in perfect equilibrium. The story appears finished, the book closed, the final page turned. But quantum mechanics whispers something interesting. In the mathematics of the very small, nothing is perfectly stable forever. What appears solid might be metastable. What seems like ground might only be a ledge, with deeper ground below. What looks like an ending might be a phase transition, a threshold, a doorway barely visible in mathematics. The silence at the end of all things might not be final. It might be pregnant with possibility, charged with potential, ready to give birth to something we cannot yet imagine. Let's explore what that might mean. We talk about heat death as an ending, the ultimate final state, the point of no return, the universe's last page. But what do we actually mean by final? In physics, final usually means stable, a state the system will remain in indefinitely. A ball at the bottom of a valley, water that's found its level, a pendulum that stops swinging. These are stable states because there's nowhere lower for them to go, no energy left to drive further change. But quantum mechanics has taught us something peculiar about stability. What appears stable might only be metastable, temporarily stable, stable enough, stable for now. And there's a world of difference between those two. Imagine a ball sitting in a bowl that's resting on a table. The ball sits peacefully at the bottom of the bowl, its local minimum the lowest point available in its immediate vicinity. From the ball's perspective, it's reached the end of its journey. It's stable, it's home. But the bowl itself sits on a table, and the table sits on a floor. The ball isn't at the absolute lowest point possible. It's at a local low point, trapped in a small valley that sits above an even deeper valley. If the ball could somehow escape the bowl, perhaps through a quantum tunnel appearing in the bowl's side, it would fall further, finding a truer, deeper stability. This is metastability, the appearance of finality that hides the possibility of further change. Quantum fields can exist in these local minima, appearing stable because there's no classical path to a lower state. But quantum mechanics doesn't require classical paths. It allows tunneling, the quantum field equivalent of walking through walls. And while the probability of such tunneling might be vanishingly small, over infinite time, vanishingly small becomes certain. The vacuum itself, and when physicists say vacuum, we don't mean empty space in the everyday sense. We mean quantum fields in their ground state, the underlying fabric of reality humming at its lowest energy. The vacuum is what empty space actually is, not nothing, but quantum fields at rest, like a still pond that's not actually still, but full of microscopic activity. The vacuum has an energy level, more specifically the Higgs field, the field that gives particles their mass, sits at a particular value throughout space. That value determines fundamental properties of our universe, the masses of electrons and quarks, the strengths of forces, the possibilities for chemistry and complexity. Current measurements place us in an interesting situation. The Higgs boson mass, measured at the Large Hadron Collider at 125 gigaelectronvolts, combined with the top quark mass at 173 gigaelectronvolts, puts our vacuum right near a boundary. These numbers suggest our universe might be metastable. Not definitely, not with certainty, but probably. The calculations have enormous uncertainties, but they point toward our vacuum being like that ball in a bowl on a table, stable enough but not absolutely stable. If we're metastable, then eventually, over timescales that make the current age of the universe look like an eye blink, the vacuum could tunnel into a lower energy state, a state with different physics, a state where the ball has finally found the floor. How long might this take? The mathematics of vacuum decay involves calculating tunneling rates through energy barriers, and the numbers that emerge are, let's just say they make a Google look modest. We're talking 10 to the power of 100 years, or 10 to the power of 1,000 years, or possibly much longer. The uncertainties are so vast that trying to pin down an exact timeline is like trying to measure the Pacific Ocean with a teaspoon. But, and this is the crucial point, the probability isn't zero, it's small, incomprehensibly small, but not zero, and given infinite time, anything with a non-zero probability becomes a certainty. It's not a question of if, but when. Though when might be so far in the future that even the dark era we explored in our last episode is just the opening credits. So what would vacuum decay actually look like? A quantum fluctuation would create a microscopic bubble, smaller than an atom, smaller than a nucleus, perhaps Planck scale small, where the Higgs field has tunneled into its true ground state. Inside this bubble, physics is different. Particle masses have changed. Forces have different strengths. The rules have been rewritten. And then, and this is where things get dramatic, the bubble expands. At the speed of light. The wall of this bubble is a moving boundary between two different types of physics, consuming the old and replacing it with the new. From inside the bubble, nothing can escape. From outside, you can't see it coming. The light that would warn you of the bubble's approach arrives at exactly the same moment as the bubble wall itself. One moment, familiar universe with familiar physics. Next moment, transformation. No warning, no escape, no survivors, because the concept of survival requires some continuity of structure, and atoms themselves don't survive the crossing. It's worth noting that this could be happening right now. A bubble of true vacuum might have nucleated billions of light years away, expanding toward us at light speed, set to arrive in 10 million years or 10 billion years. We couldn't possibly know. The universe appears stable, but that appearance tells us nothing about bubbles beyond our cosmic horizon, racing toward us through space at the maximum possible speed. Though before we panic, and really we shouldn't panic about things that won't arrive for billions of years if they arrive at all, we should remember that the universe is already nearly 14 billion years old. If vacuum decay were likely on timescales comparable to the universe's current age, it probably would have happened already. The fact that we're still here, contemplating these questions with physics that seems stable, suggests the timescale is much, much longer than the universe's current age. But in the dark era, at times measured in 10 to the power of 100 years or more, Long after black holes have evaporated and structures have dissolved, quantum fluctuations continue. Virtual particles flicker in and out of existence. And eventually, perhaps inevitably, one of those fluctuations nucleates a bubble of true vacuum. The heat-death universe, that perfectly empty, perfectly equilibrated state we contemplated in our last episode, transforms. Not slowly, but at light speed, physics resets. The rules change. New possibilities emerge from the ruins of the old. If this happens, heat-death wasn't the final state. It was just a very, very long intermission between acts. The universe's longest pause between movements. A rest that lasts longer than all previous time combined. But still just a rest, not an ending. What comes after depends on the nature of the true vacuum. Different physics means different particles, different forces, different possibilities for structure and complexity. Perhaps new forms of chemistry emerge. Perhaps new forms of energy flow. Perhaps even new forms of order we can't imagine with minds built from this vacuum's physics. Or perhaps, and this is more likely, the new vacuum is simpler, emptier, less hospitable to complexity. The ball rolling to the floor might find the floor to be a place where nothing interesting can happen, where the energy differences required for structure simply don't exist. We don't know. We can't know. The physics beyond the phase transition is literally beyond our current physics. It's like trying to understand colour while living in a black and white world, or trying to imagine a new sense you've never possessed. But the possibility remains, written in the mathematics of quantum mechanics and field theory. Nothing is perfectly stable forever. What appears final might be merely metastable, and given enough time, truly vast, profound, almost meaningless amounts of time, the metastable becomes unstable, the temporary becomes transformed, and the ending reveals itself to be a threshold. Heat-death might not be final after all. It might just be the universe catching its breath before something else begins. Imagine discovering that the ground you're standing on isn't solid earth but thin ice over a frozen ocean. You've walked on it your whole life. It's held your weight, supported civilizations, felt completely reliable. But underneath lies something different, something deeper, something you've never experienced. And if the ice ever breaks, this is the situation we might find ourselves in with the vacuum. Our vacuum, the quantum fields at their current values, the Higgs field settled where it is, appears to be a stable configuration. It's held steady for nearly 14 billion years. Every particle interaction, every chemical reaction, every biological process has operated under these rules. The vacuum seems as solid and permanent as anything could be. But quantum calculations suggest it might be what physicists call a false vacuum, stable in the local sense but not in the absolute sense. Think of it as sitting in a valley that feels like the lowest point around, while somewhere beyond the hills lies a deeper valley you can't see from where you are. The energy landscape of the Higgs field can be visualized, though we should be gentle with ourselves about the limitations of visualization when dealing with quantum field theory, as a surface where height represents energy and horizontal position represents the Higgs field value. Our vacuum sits at what appears to be a low point, but there might be an even lower point elsewhere on this landscape, separated from us by an energy barrier. Classically, we're trapped. There's no way to roll over that barrier without adding energy, and the whole point of being in a vacuum state is that there's no energy available to add. We're stuck in our valley. But quantum mechanics introduces tunneling, the quantum equivalent of the ball not rolling over the hill but appearing on the other side anyway, as if it had walked through a tunnel that doesn't classically exist. The mathematics of this was worked out by Sidney Coleman in 1977, using techniques that sound like they belong in a fantasy novel, instantons, and Euclidean time, but are actually rigorous physics. Coleman calculated the rate at which a quantum field in a false vacuum can tunnel into a true vacuum. The probability is exponentially suppressed, meaning it decreases faster than any polynomial function as the barrier gets higher. For the parameters relevant to our universe, the tunneling rate is spectacularly, almost comically small. But it's not zero. And this is where things get interesting, because not zero over infinite time means eventually certain. The transition would begin with a quantum fluctuation creating a microscopic bubble of true vacuum. This bubble would be incredibly small, typically smaller than an atom, possibly as small as the Planck length, the scale where quantum gravity effects become important, and our current theories start making uncomfortable noises about their own limitations. Inside this bubble, the Higgs field sits at its new value. The physics is different. Particle masses have changed. Electrons might be heavier or lighter, quarks differently massive. The whole cast of fundamental particles transformed the constants that determine how forces work, how chemistry operates, how structure forms, all different. And then the bubble begins to expand. Not slowly, not gradually giving us time to observe and study and prepare, at the speed of light. The bubble wall is a moving discontinuity, a shockwave in the fabric of reality itself, racing outward at the maximum speed anything can move. From inside the bubble's perspective, you're in a universe with new physics. From outside, you're in the old universe, unaware anything has changed. And the boundary between them is approaching you at light speed, which means, and this is worth sitting with for a moment, the light carrying information about the bubble's existence arrives at exactly the same moment as the bubble wall itself. No warning, no advance notice, no chance to see it coming. The observable universe, that sphere of space extending 46 billion light-years in all directions from us, would take 46 billion years to be consumed by the bubble. From inside the bubble's reference frame, though, the transition appears instantaneous. The photons carrying the image of the approaching wall don't outrace the wall because they can't. They're both moving at light speed. One moment. Familiar physics, atoms stable, chemistry working as it always has. Next moment, transition. The bubble wall itself is extraordinarily thin, quantum scale thin, but carries enormous energy density. As it passes through matter, atoms don't survive the transition in any recognizable form. The electrons, protons, and neutrons that made up your body, your planet, your galaxy, these are all patterns in quantum fields, and those fields have just changed their ground state. The patterns don't survive. The particles are reconfigured according to the new vacuum's rules. What emerges on the other side depends entirely on the nature of the true vacuum. If particle masses are very different, atoms as we know them might not form at all. If the electromagnetic force has a different strength, chemical bonds might not work. If the strong nuclear force is altered, atomic nuclei might not be stable. Most likely, though we should be appropriately uncertain about this, the new vacuum would be simpler, less hospitable to complexity. The true ground state might be a place where the energy differences required for interesting structure simply don't exist. The ball reaching the floor might find the floor to be perfectly flat, perfectly smooth, with no valleys or hills to create the energy gradients that allow things to happen. Or, and this is more speculative but mathematically possible, the new vacuum might have its own forms of complexity, its own chemistry, its own possibilities for structure, different, not necessarily simpler, just other. The energy released in the transition could be substantial. The difference between false vacuum energy and true vacuum energy, multiplied by the volume of space that's transitioned, could be enormous. More energy than all the stars have ever produced, released in the moving bubble wall, creating an intense radiation field. And once it starts, it never stops. The bubble expands at light speed forever, in all directions, consuming space, converting old physics to new, creating a pocket universe with different rules surrounded by an eternally unreachable region that still operates under the old physics. This raises an interesting question. Has this happened before? Was our Big Bang actually a vacuum decay event, a bubble of new physics nucleating within some previous universe? It's possible. The energy released in such a transition could drive a period of inflation, the exponential expansion that smoothed out the early universe, and what we call creation might have been transformation. If that's the case, somewhere beyond our cosmic horizon might lie the remnants of the previous vacuum, forever separated from us by the expansion of space, operating under different rules with its own structures and perhaps its own forms of complexity. We came from somewhere, but that somewhere is now permanently elsewhere, causally disconnected, unreachable even in principle. And if our vacuum can decay, perhaps it can decay more than once. The true vacuum we tunnel into might itself be false, metastable, capable of further decay into an even deeper ground state turtles all the way down, or rather, energy levels all the way down, each vacuum decaying into another, each with its own physics, an infinite cascade of possibilities. Fortunately, if we can use that word for something that won't matter for 10 to the power of 100 years or more, there's no indication this is happening in our immediate cosmic neighborhood. We've existed for nearly 14 billion years without experiencing vacuum decay, which tells us the tunneling rate must be very, very slow. The lifetime of our vacuum is much longer than the current age of the universe. Though here's a thought that might interfere with sleep if we let it. The bubble could have already nucleated. Somewhere 10 billion light-years away, or 20 billion, or 100 billion, well beyond our cosmic horizon, a bubble of true vacuum could have appeared and begun expanding, racing toward us at light speed, set to arrive in 10 billion years or 50 billion years, or whenever the expanding wall happens to reach this particular corner of space. We wouldn't know, couldn't know. The universe appears stable because the parts we can see haven't yet been reached. The instability is coming, but it's coming at the same speed as the light. That would warn us of its approach. But we shouldn't lose too much sleep over this. The probability of such an event on human-relevant timescales is so small, it makes winning the lottery every day for a year look like a safe bet. The universe has survived for nearly 14 billion years. The laws of physics have held steady through the formation of galaxies, stars, planets, and life. That longevity suggests our vacuum is either truly stable or metastable, with a lifetime vastly longer than the current age of the cosmos. In the context of the Dark Era, our heat-death future, that empty, equilibrated state we explored in our last episode, vacuum decay takes on a different character, at times measured in 10 to the power of 106 years, long after black holes have evaporated and structures have dissolved. The universe sits in near-perfect emptiness. Particles are separated by light years. Temperature hovers just above absolute zero. Nothing much happens because there's nothing much left to happen with. But quantum fluctuations continue. Virtual particles flicker into existence and vanish, and occasionally, very, very occasionally, one of those fluctuations might nucleate a bubble of true vacuum. The bubble expands through essentially empty space. There's almost nothing for the wall to encounter, A few scattered photons, perhaps an electron, some dark matter particles if they haven't decayed. When the wall does encounter matter, that matter is reconfigured according to new rules. From a cosmic perspective, this might be the ultimate transformation. The heat-death state, that seemingly final equilibrium, gets replaced by new physics, new possibilities, new forms of energy distribution. The universe doesn't end so much as reset, changing its fundamental operating system. Multiple bubbles could nucleate in different locations, expanding until they collide. Where two bubbles meet, you'd have a boundary between two different types of new physics, creating complex structures in the collision zone. The universe could become a patchwork of different vacua, each region operating under its own rules, separated by boundaries where the physics changes. Some cosmologists have looked for evidence of such collisions in our past. If our observable universe formed inside a bubble that later collided with another bubble, there might be signatures in the cosmic microwave background, circular patterns, temperature discontinuities, preferred directions. Searches have found nothing conclusive. Some tantalizing hints, perhaps, but nothing that couldn't be explained by other processes or statistical fluctuations. The mathematics of vacuum decay was extended in 1980 by Sidney Coleman and Frank DeLucia to include the effects of gravity and curved space-time. They found that in an expanding universe like ours, the expansion actually helps stabilize the vacuum. The rate of bubble nucleation is even lower than it would be in flat space-time. But even lower still isn't zero, just smaller. The transition from incomprehensibly unlikely to even more incomprehensibly unlikely. A comfort, if you can call it that, measured in additional zeros added to already absurd timescales. There's something both terrifying and fascinating about vacuum decay. Terrifying because it represents the end of everything we know, not just structures and objects, but the very rules that allow those structures to exist. The laws of physics themselves are rewritten. Chemistry becomes impossible or becomes different. Biology becomes meaningless. Everything built on the current vacuum's physics simply stops being possible. But fascinating because it represents transformation rather than heat death. Instead of the universe fading into unchangeable equilibrium, it transforms into something new. The rules change. New possibilities emerge. The cosmos gets a fresh start, albeit one we wouldn't survive to witness. The Greek philosopher Heraclitus said, "Everything flows, nothing stands still." Vacuum decay takes this to its absolute limit. Even the ground state flows. Even the laws themselves change. Even the vacuum, the very fabric of empty space, transforms. Stability becomes revealed as temporary, permanence as illusion. The heat death that seemed so final might be just the universe catching its breath before the next transformation. And if consciousness somehow persisted, which it almost certainly wouldn't, but let's imagine anyway, what would it be like to experience reality itself changing? To watch the fundamental constants shift, particles transform, forces reconfigure? It would be like watching the rules of mathematics change mid-calculation, the laws of logic rewrite themselves, the nature of existence becomes suddenly negotiable. We can't survive it. Our atoms wouldn't make it through the transition. Our patterns wouldn't persist in the new physics. But the universe survives, transformed, ready to explore whatever possibilities the new vacuum allows. Heat death isn't final. It's a phase transition, a threshold, the end of one chapter and the beginning of another, written in different physics, operating under different rules, exploring different possibilities, in the infinite space of what quantum fields can do. The silence at the end of all things might be broken by the most fundamental transformation imaginable, reality itself deciding to be different. What if the universe is not a single, isolated entity, but a member of a family? What if space-time itself can reproduce, budding off offspring universes that inherit some properties but develop independently? This sounds like it belongs in science fiction, perhaps in a novel where reality itself has become implausibly fertile. But it's serious physics, proposals grounded in quantum mechanics and general relativity, attempting to understand whether nothing can give birth to something. The foundation for these ideas comes from quantum cosmology, which does something that initially seems absurd. It applies quantum mechanics to the entire universe. In normal quantum mechanics, we describe particles with wave functions that give probabilities for different states. In quantum cosmology, we describe the universe itself with a wave function that gives probabilities for different space-time geometries. The equation governing this is called the Wheeler-DeWitt equation, named after John Wheeler and Bryce DeWitt, who developed it in the 1960s. It's essentially the Schrödinger equation applied to the universe, but with a peculiar feature. It has no external time parameter. Time doesn't appear in the equation as an independent variable because there's nothing outside the universe to measure time against. Instead, time emerges from the solutions themselves, from the internal relationships between different parts of the wave function. This leads to a strange implication. The universe exists in a quantum superposition of all possible geometries simultaneously. It's only when we, observers inside the universe, make measurements that we experience one particular geometry, one particular history. From the outside, if such a perspective made sense, the universe would be all of its possibilities at once. In 1983, James Hartley and Stephen Hawking proposed what they called the no-boundary proposal for the origin of the universe. They asked what seems like a simple question: what came before the Big Bang? Their answer was elegant. The question is meaningless, like asking what's north of the North Pole. At the North Pole, all directions are south. There is no north. Similarly, at the Big Bang, there is no before. They showed this using a mathematical trick involving imaginary time multiplied by the square root of -1, which sounds mystical but is actually just a standard technique in quantum mechanics. In imaginary time, space-time becomes Euclidean, like the surface of a sphere, smooth, continuous, with no edges or boundaries. Time begins at the Big Bang, not because something caused it to begin, but because that's simply where time starts, just as north starts to have meaning as you move away from the North Pole. In real time, the time we experience, the universe evolves from the Big Bang, expanding and cooling, but in imaginary time it exists as a complete four-dimensional object, a closed surface with no boundary, no edge, no moment of creation requiring explanation. The universe is self-contained, needing no external cause. Alexander Vilenkin, working around the same time in 1982, proposed a different scenario. Instead of having no boundary, the universe tunnels into existence from literally nothing, not nothing in the sense of empty space, but nothing in the sense of no space, no time, no fields. Absolute nothingness, a state so empty it doesn't even count as a state. The mathematics describes a quantum tunneling event where a small, inflating patch of space-time spontaneously appears. The probability is exponentially suppressed, meaning it's incredibly unlikely at any given moment. But here's the thing about moments when there's no time. The concept becomes slippery. In a timeless state, does unlikely even mean anything? These ideas suggest that universes can tunnel into existence through quantum processes. And if it can happen once, our universe coming into being, why couldn't it happen again? Why couldn't our universe give birth to baby universes through similar quantum tunneling events? This is where wormholes enter the picture. In general relativity, wormholes are theoretical tunnels connecting distant regions of space-time, or potentially connecting different universes altogether. Einstein and Nathan Rosen discovered them mathematically in 1935, though they're usually called Einstein-Rosen bridges. The geometry is strange but mathematically consistent. You enter one mouth of the wormhole and emerge from another, possibly light years away, possibly in another universe entirely. At the quantum scale, the Planck scale, where distances are around 10 to the power of minus 35 meters, space-time might be filled with virtual wormholes, constantly appearing and disappearing in what John Wheeler poetically called quantum foam. This isn't established physics, but it's a reasonable extrapolation of quantum mechanics applied to gravity at the smallest scales. If these virtual wormholes exist, occasionally one might expand rather than collapse, might grow large enough to become a new universe, connected to our universe by an umbilical wormhole. From our perspective, it might look like a black hole, matter falling in, nothing coming out. From inside, it looks like an expanding universe with its own space and time. This leads to a fascinating possibility about black holes. When matter collapses into a black hole, it crosses the event horizon and disappears from our observable universe. But what happens to it inside? The classical answer is that it falls toward the singularity at the center, where densities become infinite and our theories break down. But perhaps that's not the whole story. Perhaps the interior of a black hole is actually a separate universe, expanding in its own right, with its own space and time. From outside, we see a black hole. From inside, observers would see, well, they'd see a universe, their universe, which happens to be inside what we call a black hole. This isn't completely wild speculation. The mathematics of black hole interiors can be extended in ways that make the interior look remarkably like an expanding universe. The connection isn't proven, but it's tantalizing. Every black hole might be a doorway to another cosmos. Lee Smolin, a theoretical physicist, took this idea and added an evolutionary twist. If black holes create baby universes, and those baby universes inherit properties from their parent universe with slight random variations, like cosmic DNA with mutations, then you get a selection process. Universes that produce more black holes will have more offspring. Over many generations, universes would evolve toward producing the maximum number of black holes. This could explain the fine-tuning of physical constants. Why are the laws of physics just right for stars and galaxies, and, coincidentally, for life? Perhaps because stars are factories that produce black holes. Universes good at making stars reproduce more. We find ourselves in such a universe not because we're special, but because universes like ours are common in the cosmic family tree. They're successful reproducers. Smolin's cosmological natural selection makes testable predictions. If universes are optimized for black hole production, stellar masses should be near the maximum that still allows black hole formation. Change the constant slightly, and you'd get fewer black holes. Current observations are consistent with this, though not definitively confirmatory. The idea remains speculative but intriguing. In the context of eternal inflation, which we'll explore more in the next chapter, baby universes take on another meaning. Inflation is the exponential expansion thought to have occurred in the first fraction of a second after the Big Bang. In some regions, inflation ends and normal expansion begins. Those regions become pocket universes like ours. But in other regions, inflation continues, creating more space, which allows more regions where inflation might end, creating more pockets in a process that never globally terminates. Each pocket universe is a baby universe, born from the inflating space around it. The multiverse becomes a fractal structure, with universes budding off universes, nested within inflating space, creating an infinite tree of possibilities. Baby universes might form in other ways too. Quantum fluctuations in the heat-death era could, given enough time, spontaneously create inflating regions. The probability is phenomenally small, but over 10 to the power of 100 years or more, the improbable becomes routine. The heat-death state might not be sterile but fertile, capable of birthing new cosmos through quantum tunneling events. What would such a birth look like? A region of space, perhaps just Planck scale initially, where quantum fluctuations create an inflating patch. That patch expands exponentially, creating its own space, its own time, eventually disconnecting from the parent universe to become independent. The parent universe might notice nothing, just a brief fluctuation, a quantum hiccup. The baby universe experiences its own Big Bang, its own cosmic history, potentially lasting billions of years. Information might transfer from parent to offspring. If a baby universe forms from matter falling into a black hole, the information encoded in that matter might somehow imprint on the baby universe's initial conditions. This would be a resolution to the black hole information paradox. Information doesn't get destroyed at the singularity, it gets transferred to the offspring universe. This is highly speculative, of course. We're stacking maybes on top of perhapses on top of possibles. But the mathematics is consistent, the physics not obviously wrong, the implications profound. Could we ever detect baby universes forming? Direct observation seems impossible. Once a baby universe disconnects from ours, we can never see it or communicate with it. But indirect evidence might exist. If baby universes formed in our cosmic past, they might have left signatures in the cosmic microwave background patterns, asymmetries, preferred directions pointing toward the umbilical connections that once existed, but have since stretched beyond detection. So far we haven't found such signatures, but the absence of evidence isn't evidence of absence, merely evidence that we haven't looked carefully enough, or that the signatures are too subtle for our current instruments. There's something philosophically interesting about this picture of reality. Instead of a single, lonely universe adrift in nothingness, we have a cosmos that's alive with possibility, fertile, reproductive universes budding from universes, each with its own laws, or laws similar to their parents, with variations. Cosmic evolution operating at the grandest possible scale. The heat death we contemplated in our last episode becomes less final in this picture. Yes, our universe might reach maximum entropy, structures dissolving, change ceasing, but that dead universe might still be capable of giving birth. Quantum fluctuations could nucleate baby universes even in the heat-death state. The parent might be cold and empty, but the children could be vibrant and full of possibility. It's a beautiful reversal of our usual intuitions about death and birth. We think of birth requiring vitality, energy, life, but in quantum cosmology, birth requires only the laws of physics and enough time. The cold, empty universe becomes a womb for new cosmos, each beginning its own journey from Big Bang to heat death, possibly producing offspring of their own along the way. The universe might not be an isolated event, but a member of an infinite family tree, with ancestors we can't see and descendants we'll never know, all connected through the quantum foam, all budding from the fertile void. Nothing turns out to be pregnant with possibility. The vacuum isn't empty but active, capable of creation, ready to birth something from the apparent absence of anything. The silence at the end of all things might not be sterile but generative, not final but transitional. And somewhere in the mathematics of quantum mechanics and general relativity, in the equations describing how space-time curves and fields fluctuate, lies the mechanism by which nothing becomes something, by which endings become beginnings, by which the universe proves itself capable of the most fundamental magic of all, creation from the void. Imagine you're standing in a field during a rainstorm. Each raindrop that hits the ground creates ripples in a puddle. Now, imagine the rain never stops. It's been falling forever, will fall forever. Infinite raindrops creating infinite ripples in infinite puddles. Each ripple a self-contained pattern spreading outward, interacting with others, creating complexity from simple falling water. Our universe might be one such ripple, formed when cosmic inflation rained down on a particular region of space-time. And the rain continues, has always continued, will always continue, creating infinite universes in an eternally inflating megaverse. Our heat death becomes just one ripple's fade, while the rain keeps falling everywhere else. To understand eternal inflation, we need to start with regular inflation, the brief period of exponential expansion thought to have occurred in the first fraction of a second after our Big Bang. Alan Guth proposed this in 1981 to solve several puzzles about the early universe. Why is space so flat? Why is the cosmic microwave background so uniform across regions that shouldn't have been in causal contact? Why don't we see magnetic monopoles, which particle physics predicts should have been created in the early universe? Inflation solves all of these elegantly. A brief period of exponential expansion from around 10 to the power of minus 36 seconds to 10 to the power of minus 32 seconds after the Big Bang stretches space by an enormous factor, perhaps 10 to the power of 26 or more. This flattens any initial curvature, smooths out any irregularities, and dilutes any unwanted relics to undetectable densities. The mechanism driving inflation is a scalar field called the inflaton, a quantum field permeating space, similar in concept to the Higgs field. This field has potential energy, like a ball sitting on a hill. As the field slowly rolls down its potential energy curve toward lower values, the energy stored in the field drives exponential expansion of space. When the inflaton field reaches the bottom of its potential, finds its minimum energy state, inflation ends. The field oscillates around this minimum, its energy decays into particles, and the universe reheats to a high temperature. This reheating is what we call the Big Bang from our perspective. Inflation comes before the Big Bang, setting up the initial conditions that the Big Bang works with. This is the standard picture. Inflation starts, runs for a brief period, ends, and normal expansion begins. Our entire observable universe formed from one inflating patch that stopped inflating and reheated. But here's where things get interesting. The inflaton field is subject to quantum fluctuations. As it slowly rolls down its potential, quantum mechanics causes its value to fluctuate randomly in different regions of space. In some regions, these fluctuations push the field downward toward the minimum, causing inflation to end. But in other regions, the fluctuations push the field upward, back up the hill, giving it more energy and causing inflation to continue. The crucial question is, which effect dominates? Does inflation end faster than new inflating regions are created, or does it create new inflating regions faster than it ends? Andre Linde, working in the 1980s, showed that under reasonable conditions inflation never ends globally. Yes, it ends in some regions. those regions become pocket universes like ours, but it continues in other regions, creating more space, which allows more quantum fluctuations, which creates more regions where inflation ends and more regions where it continues, in a process that feeds itself forever. Once eternal inflation starts, it never stops. It's eternal to the future, always creating new pocket universes, always spawning new inflating regions, a process without end. Picture it this way: inflation is like a river that occasionally splits into streams. Some streams dry up. Those are pocket universes where inflation has ended. But the main river keeps flowing, splitting into more streams, some of which dry up while others keep flowing and splitting. The river network grows forever, with an ever-increasing number of streams at any given time. Our observable universe is one dried-up stream. Inflation ended here 13.8 billion years ago. Space stopped expanding exponentially and started expanding normally. Matter and energy condensed from the reheating. Structures formed. We happened. But elsewhere, perhaps just beyond our cosmic horizon, perhaps vastly farther away than we can imagine, inflation continues. Space expands exponentially in those regions, stretching by factors of 10 to the power of 26 every fraction of a second, creating volume, creating possibilities, creating new regions where inflation might end, producing new pocket universes with their own big bangs, their own cosmic histories. The number of pocket universes in eternal inflation is infinite, not just very large, actually infinite. Each one is causally disconnected from all the others, separated by inflating regions expanding faster than light can cross them. Each one potentially has different properties, different physical constants, different laws of physics. This is where string theory enters the conversation, offering what physicists call the landscape. String theory, in its attempts to be a theory of everything, produces not one unique set of physical laws, but roughly 10 to the power of 500 different possible vacuum states. Different ways the extra dimensions of string theory can curl up, each giving different low-energy physics. If string theory is correct, and if eternal inflation is correct, then the landscape gets populated. Each pocket universe randomly selects one of those 10 to the power of 500 possible vacua. Different pockets get different physics, different particle masses, different force strengths, different cosmological constants. The full range of possibilities gets explored, not in one universe, but across the infinite collection. Most of these possibilities are hostile to complexity. Wrong constants, wrong forces, no stable atoms, no chemistry, nothing interesting. But with 10 to the power of 500 possibilities and infinite pockets to explore them, some fraction, possibly a large fraction, will have conditions suitable for complexity, for stars and planets, for chemistry and life, for observers. This provides an explanation for fine-tuning that's been bothering physicists for decades. Why are the laws of physics so precisely calibrated for life? Why is the cosmological constant so small? Why are particle masses in such a narrow range? The anthropic answer: they're not special. Most universes have different values. We find ourselves in one of the rare universes with the right values, because only those universes can contain observers. It's selection bias on a cosmic scale. This resolves the fine-tuning problem by making it inevitable. With infinite universes exploring all possibilities, some will have the right conditions. Those are the only ones where anyone exists to ask why the conditions are right. But eternal inflation creates some conceptual problems, particularly around probability. In eternal inflation, everything happens infinitely often. Infinite universes where intelligent life evolves. Infinite universes where it doesn't. infinite universes where the laws of physics are like ours, and infinite universes where they're different. How do you calculate probabilities when everything has infinite measure? If you ask, what's the probability of observing fine-tuned constants? The naive answer is infinity divided by infinity, which is undefined. You need some way to regulate the infinities, to compare infinite sets, to define what typical means in an infinite multiverse. This is called the measure problem, and it's unsolved. Different proposals exist, different ways to define probability measures on the infinite multiverse, but they give different predictions, and there's no consensus on which is correct. It's a genuine theoretical challenge, one that suggests our understanding of eternal inflation is still incomplete. There's also the Boltzmann brain problem, which might be the strangest prediction of eternal inflation. A Boltzmann brain is a conscious observer that forms spontaneously from random quantum fluctuations, rather than through evolution. In an infinite universe with infinite time, random fluctuations will occasionally assemble matter into a functioning brain with false memories of a past that never happened. Here's the problem. In eternal inflation, Boltzmann brains should vastly outnumber evolved observers. It's much easier for random fluctuations to create just a brain than to create an entire universe with stars and planets and evolution. So statistically, if you're an observer in the multiverse, you're probably a Boltzmann brain with false memories, not an actual evolved human. This is clearly absurd. You're not a Boltzmann brain, probably, which suggests something is wrong with the reasoning. Either the probability measure we're using is incorrect, or eternal inflation itself has problems, or there's some selection effect we're not understanding. It's an active area of research and disagreement. Despite these conceptual challenges, eternal inflation has attractive features. It explains the initial conditions of our Big Bang. It provides a mechanism for exploring the landscape of possible physics. It makes inflation, which already has strong observational support from cosmic microwave background observations, even more robust by making it eternal. And it changes the meaning of our heat death. In our pocket universe, yes, entropy increases, structures dissolve, temperature drops to near absolute zero. The heat death arrives after 10 to the power of 100 years or more, and our pocket becomes cold, empty, unchanging. But globally, nothing ends. Inflation continues elsewhere, creating new pockets, each with its own cosmic history. While our pocket fades, others are just beginning their journeys from Big Bang to heat death. The multiverse as a whole is in a steady state, always inflating regions, always forming pockets, always pockets reaching heat death, balanced in a process that never globally terminates. It's like a forest where individual trees grow, age and die, but the forest as a whole maintains a stable population. Our tree is dying, but countless others are sprouting, growing, creating their own canopies and ecosystems. The forest is eternal, even though every tree is mortal. This raises the question of beginnings. If eternal inflation is eternal to the future, what about the past? Did it have a beginning, or has it been running forever? The mathematics suggests it probably had a beginning. Arvind Borde, Alan Guth and Alexander Vilenkin proved a theorem showing that eternal inflation cannot be past eternal. It must have started somewhere, sometime. You need some initial inflating patch, however small, to get the process going. But where did that come from? Perhaps from quantum tunneling out of nothing, as Vilenkin proposed. Perhaps from a previous phase of contraction. Perhaps from some other mechanism we haven't imagined yet. The question of absolute origins remains open. Eternal inflation or not? In the context of our earlier discussions about vacuum decay and baby universes, eternal inflation provides a framework where all these processes might occur simultaneously. Some pockets might undergo vacuum decay, transitioning to different physics. Some might spawn baby universes through quantum tunneling. Some might reach heat death peacefully. The multiverse explores all possibilities because it has infinite space and infinite time to do so. Our observable universe, that sphere of space 46 billion light-years in radius, containing everything we can possibly see, is vanishingly small compared to our pocket universe, which might be infinite in size, and our pocket universe is just one of infinitely many, and the entire multiverse is eternally generating more. We exist in nested infinities, observable universe within pocket universe within eternally inflating multiverse, each scale vastly larger than the one before, each making the previous scale seem infinitesimal. It's simultaneously humbling and magnificent. Humbling because it places us in an inconceivably small corner of reality, one pocket among infinite pockets, one observer among infinite observers, most of whom we can never meet or communicate with because the space between us is expanding too fast, but magnificent because we're part of this grand structure, capable of understanding our place in it, able to do the mathematics that reveals these nested infinities. The Copernican principle gets extended to its ultimate conclusion. We're not special spatially. Earth isn't the center of anything. We're not special temporally. Our moment isn't privileged. We're not special physically. The same laws operate everywhere in our pocket, and now we're not special universally. Our pocket is one of infinitely many, each with potentially different physics, each playing out its own story. Yet here's a strange comfort. In an infinite multiverse exploring all possibilities, everything that can happen does happen. Somewhere, in some pocket, there's a version of events where every possibility gets explored. Not in our pocket, necessarily, but somewhere in the infinite collection. The heat death of our universe becomes less significant in this view. Yes, locally it matters. It's our ending, the conclusion of our cosmic story. But globally, it's just one event among infinite events, one ending among infinite endings and beginnings, a single note in a symphony that never stops playing. The rain keeps falling, new ripples keep forming, and while our ripple fades, the pattern continues elsewhere forever in an eternal inflation that transforms the question, what comes after the end, into which ending are we talking about? Our end is not the end, just an end, one of infinitely many. What if the heat death isn't an ending but a transition, not to a different place, but to a different time? What if the universe's far future is also its distant past? Roger Penrose, one of the greatest mathematical physicists alive, winner of the 2020 Nobel Prize for his work on black holes, proposes something quietly radical, that our Big Bang was the heat death of a previous universe, and our heat death will become the Big Bang of the next. Time is cyclic, but not repetitive. Each cycle, or aeon, as Penrose calls them, is unique, yet connected to those before and after through a boundary that is simultaneously ending and beginning. The death of one universe becomes the birth of another, not through catastrophe, but through a peculiar mathematical transformation. To understand conformal, cyclic cosmology, usually abbreviated CCC, which is easier on the tongue, we need to understand what conformal means. A conformal transformation is a mathematical operation that rescales distances while preserving angles. Imagine looking at a photograph and zooming in or out. The shapes stay the same, the angles between lines remain unchanged, but the overall scale changes. That's a conformal transformation. In physics, conformal transformations change the metric of space-time, the mathematical object that tells you how to measure distances and times, but leave the causal structure intact. Light cones don't change shape. The relationships between events remain the same. Only the scale changes, which sounds trivial until you realize that in some circumstances, scale becomes ambiguous. Consider the heat-death state of the universe in the far future. We've explored this. After 10 to the power of 100 years or more, black holes have evaporated. Matter has decayed or become so dilute it's essentially absent. Only massless particles remain. Photons travelling through ever-expanding space, perhaps a massless gravitinos if supersymmetry is correct, nothing else. Here's the interesting thing about massless particles. They don't experience time. From a photon's perspective, if such a perspective made sense, its emission and absorption happen at the same instant, regardless of how far it travels. Massless particles have no rest frame, no internal clock, no way to measure time. When only massless particles remain, the universe has no natural way to define time or scale. There are no clocks, no rulers, no reference points. Time becomes ambiguous. Scale becomes arbitrary. Now consider the very early universe, just after the Big Bang. Temperatures are so extreme that all particles are effectively massless. They're moving too fast, have too much energy for their rest mass to matter. The universe is radiation-dominated, filled with massless particles zipping around at light speed. Again, no rest frames, no clocks. Time and scale are ambiguous. Penrose's insight, these two states, the heat-death of one aeon and the Big Bang of the next, are conformally equivalent. They have the same structure when you ignore scale. The hot, dense, small early universe, and the cold, empty, large late universe look the same if you perform the right conformal rescaling. Small and hot becomes large and cold through a simple mathematical transformation. The heat-death, stretched and rescaled, becomes the Big Bang. The ending of one aeon transforms into the beginning of the next, smoothly, without a singularity, through conformal geometry. But there's a catch. Not everything can be conformally equivalent. Mass breaks the symmetry. Massive particles have rest frames and natural timescales. For the transition to work, all massive particles must be gone by the heat-death. Fortunately, in standard cosmology, this eventually happens. Protons might decay after 10 to the power of 34 years. Black holes evaporate through Hawking radiation. Given enough time, everything massive either decays or falls into black holes which then evaporate. There's another requirement, more subtle. The Weyl curvature of spacetime must vanish at both boundaries. Spacetime curvature comes in two types. Ricci curvature, which is related to energy and momentum, and Weyl curvature, which represents tidal forces and gravitational waves. At the Big Bang, the Weyl curvature is observed to be very small, almost zero, which is actually rather mysterious and requires explanation. At the heat-death, after black holes have evaporated, Penrose argues the Weyl curvature returns to zero. Why? Black holes carry enormous Weyl curvature, their gravitational fields, tidal forces made concrete, but when they evaporate through Hawking radiation, that curvature dissipates. The radiation spreads out, redshifts, becomes diluted by expansion. Eventually the Weyl curvature approaches zero again, leaving spacetime smooth and flat, just as it was at the Big Bang. This matching of Weyl curvature at the beginning and end allows the conformal connection. Both boundaries have the same geometric structure. Zero Weyl curvature, massless content, ambiguous time and scale. They can be mathematically identified, one becoming the other through conformal rescaling. Imagine walking on a sphere, starting at the North Pole, travelling south, reaching the South Pole. Now imagine that through some coordinate transformation, the South Pole you reached is identified with a different North Pole, not the one you started from, but the beginning of a new sphere. You step from the end of one sphere to the beginning of the next, and continue walking. That's 300. The end of one aeon is the beginning of the next. Time is cyclic, but each cycle is a different sphere, a different universe, with its own history. What happens to entropy in this picture? That's the tricky part. In standard thermodynamics, entropy always increases. The second law is inviolable. But at the transition between aeons, does entropy reset? Does it somehow return to a low value to begin the next cycle? Penrose's answer is subtle. He argues that entropy is a measure of information about distinguishable states, and in the heat-death, when only massless particles remain, there are no clocks to distinguish different states. Time becomes meaningless. Entropy, which requires time to have meaning, becomes ambiguous. At the transition, it's not that entropy resets in violation of thermodynamics, but that the concept loses applicability and then reacquires it with new meaning in the next aeon. Most physicists find this argument, let's say, not entirely convincing. The entropy problem remains the biggest conceptual challenge for CCC. How can a high entropy state become a low entropy state without violating the second law? Penrose's appeal to the meaninglessness of entropy in the massless limit is clever, but it doesn't satisfy everyone. Still, the mathematics works. The conformal structure matches, and CCC makes testable predictions, which is more than can be said for many speculative cosmologies. The predictions involve gravitational waves. If massive black holes collided in the previous aeon, they would have created powerful gravitational waves. These waves would propagate through the transition into our aeon, leaving imprints in the cosmic microwave background, the earliest light we can observe. Specifically, CCC predicts concentric circles of correlated temperature fluctuations in the CMB. These circles would mark the spots where gravitational waves from black hole collisions in the previous aeon crossed into ours. Several research groups have searched for these circles. Some claim to have found them, others dispute the findings, suggesting the patterns could be statistical flukes or systematic errors in the analysis. As of now, the evidence is marginal at best. The circles, if they exist, are subtle and controversial. The cosmic microwave background contains lots of patterns, and it's easy to see patterns that aren't really there, especially if you're looking for them. The scientific community remains skeptical, though not dismissive. There's also the prediction of Hawking points, slightly warmer spots in the CMB corresponding to the final Hawking radiation from evaporating black holes in the previous eon. Again, some researchers claim to see these. Again, most remain unconvinced. The jury is very much still out. What's appealing about CCC is its elegance. It solves the problem of the beginning. There's no absolute beginning, just an infinite sequence of aeons stretching into the past. It solves the problem of the end. Heat-death isn't final, just a transition. It explains why the whale curvature is so low at the Big Bang, because it has to match the low whale curvature at the end of the previous aeon. Each aeon is unique. Different structures form, different galaxies appear, different stars shine. It's not Nietzsche's eternal recurrence, the same events repeating forever, which sounds philosophically interesting but physically implausible. Instead, it's eternal variation, similar physics, different outcomes, infinite diversity across infinite cycles. Information might carry across aeons in the form of gravitational waves. The violent events of one aeon, black hole collisions, the final mergers of supermassive black holes at galaxy centers, leave traces in the next not detailed information, not enough to reconstruct what happened, but echoes, shadows of the previous universe lingering in ours. There's something poetic about this. The past doesn't vanish but persists as vibrations in space-time, ripples in the geometry itself, whispering stories about what came before to anyone who knows how to listen. And if 330 is correct, our universe will do the same. The black holes we're forming now, from stellar collapse from galactic mergers, will eventually evaporate, but before they do, they might collide, merge, create gravitational waves. Those waves will propagate through the heat death, through the conformal transition into the next aeon, where observers, if observers exist there, might detect them as circles in their cosmic microwave background, wondering what kind of universe came before them. The philosophical implications are interesting. In most cosmologies, we face either an absolute beginning that requires explanation but can't have one, or an infinite past that seems conceptually uncomfortable. CCC offers a middle path. No absolute beginning, but not an unchanging infinite past either. Time is eternal but structured into distinct aeons, each with a definite beginning and end, yet connected to those before and after. It's reminiscent of Hindu cosmology, with its cycles of creation and dissolution, days and nights of Brahma, the universe breathing in and out across vast timescales, or Buddhist cosmology, with its endless cycles of birth and death, each life connected to but distinct from the previous ones. Ancient wisdom meeting modern physics, though with very different timescales, 10 to the power of 100 years rather than thousands or millions. The main criticism beyond the entropy problem is that it feels too convenient. The universe has to be just right at heat death, all massive particles gone, well curvature at zero, conditions perfect for the conformal transition. Any deviation, and it doesn't work. This requires either fine-tuning, which we generally try to avoid in physics, or some mechanism ensuring the conditions are met, which hasn't been fully worked out. Still, CCC remains one of the most developed cyclic cosmologies we have. Penrose is a serious physicist with a track record of profound insights. He predicted key features of black holes decades before they were observed. His ideas deserve attention, even if they're not widely accepted. And there's something deeply satisfying about a cosmology where endings become beginnings, where death leads to rebirth, where the heat death we've been contemplating, that cold, empty, silent state, transforms into the hot, dense, energetic Big Bang of a new aeon. It means our ending isn't final. Our heat death becomes someone else's beginning. The structures we build, the atoms we arrange, the patterns we create, all of this decays, dissolves, disappears. But the gravitational waves we produce, the space-time ripples from the most violent events in our cosmic history, those persist. Not forever. Nothing persists forever in CCC. But long enough to cross into the next cycle, to tell the next universe that something came before. Time becomes a spiral rather than a line, always moving forward, never repeating, but returning to similar states. The universe not as a story with beginning and end, but as a wheel that turns, each rotation unique yet similar to those before. The heat death might not be darkness descending but dawn breaking, not an end but a threshold, not silence falling but a new voice beginning to speak, continuing a conversation that has been going on forever and will continue forever. Each aeon adding its verse to an endless poem written in the geometry of space-time itself. Whether CCC is correct remains an open question, but it's a beautiful question, one that transforms the heat death from finality into possibility, from ending into transition, from death into a peculiar form of rebirth. We experience time as flowing in one direction, from past through present toward future. Memories point backward, causality flows forward, entropy increases, we age, eggs break, coffee cools. The arrow of time seems fundamental to existence, as basic as space itself. But here's something peculiar. The fundamental laws of physics don't distinguish past from future. Newton's laws work equally well forward or backward in time. Maxwell's equations describing electromagnetism are time-symmetric. Even the Schrödinger equation governing quantum mechanics is reversible. General relativity treats time as just another dimension, with no preferred direction built into the mathematics. If the laws are symmetric, why does time have an arrow? And more relevant to our journey, could that arrow reverse, restart, or cease entirely in the far future? The arrow of time we experience is thermodynamic. It comes from the second law of thermodynamics. Entropy increases in closed systems. This defines forward in time as the direction toward higher entropy. Broken eggs don't spontaneously reassemble. Mixed coffee doesn't unmix itself. Heat flows from hot to cold, never the reverse. This irreversibility gives time its direction. But the thermodynamic arrow isn't fundamental. It emerges from statistics and initial conditions. The individual particles in a broken egg follow time-symmetric laws. Yet collectively, they move toward higher entropy because there are vastly more ways to be broken than to be whole. The arrow emerges from probability, from the fact that the universe started in a low entropy state, and entropy has been increasing ever since. This starting point, the Big Bang, is crucial. The universe began in a remarkably organized state. Hot, yes. Dense, yes. But also incredibly smooth and uniform, with very low entropy for its energy content. This initial low entropy is what we call the past hypothesis, a boundary condition not explained by the laws of physics themselves that breaks time symmetry and creates the arrow we experience. Everything follows from this. Entropy increases, structure forms and then decays. Stars shine and die. We're born, live, and pass away. All because the universe started with low entropy and has been sliding toward higher entropy ever since. At heat death, entropy reaches its maximum. There are no more gradients, no hot and cold, no organized and chaotic, no structured and diffuse, everything has equilibrated. And without entropy gradients, there's no thermodynamic arrow. The distinction between past and future becomes unclear. Time still exists mathematically. The equations still work. Space still expands. But physically, what does time mean when nothing changes? A clock requires change to measure. Memory requires the formation of records, which increases entropy. Causality requires events to be distinguishable from one another. In maximum entropy, these requirements aren't met. Time continues as a parameter in the equations, but it loses its physical meaning. Past and future become symmetric again, not because the laws have changed, but because the thermodynamic arrow has disappeared. Does this mean time stops? Not exactly. It means time becomes directionless, like being at the North Pole where all directions are south at maximum entropy. All directions in time are equivalent. The flow we experience, past to future, depends on entropy increase. Without that increase, the flow stops having meaning. Could time reverse? It's an old idea. Thomas Gold proposed in 1962 that if the universe eventually contracts, entropy might decrease during the contraction phase, reversing the arrow of time. In expansion, time flows one way. In contraction, it flows the other. At the turnaround point, maximum expansion, time would reverse direction. It's a fascinating thought experiment, but probably wrong. The second law of thermodynamics is extremely robust. Entropy increase isn't just likely, it's overwhelmingly likely given any reasonable initial conditions. Reversing it would require an implausibly precise coordination of every particle in the universe, all spontaneously organizing themselves into lower entropy configurations. The probability isn't quite zero, but it's close enough that calling it impossible seems fair. Even if the universe contracts, entropy would most likely continue increasing during the contraction. Time would keep flowing in the same direction toward higher entropy, which now means toward the Big Crunch rather than away from the Big Bang. The arrow doesn't reverse. It just points toward a different endpoint. There's another possibility, more subtle, that time isn't fundamental at all, but emergent from something deeper. Some approaches to quantum gravity, particularly the Wheeler-DeWitt equation we mentioned earlier, describe the universe in a timeless way. Time emerges from correlations between different parts of the system, from entanglement between clocks and the systems they measure. If time is emergent, what happens when those correlations disappear? At heat death, with maximum entropy and minimal structure, perhaps the entanglement that generates experience time fades away. Not that time stops, but that the phenomenon we experience as time, the sense of flow, of before and after, emerges from structure and entropy gradients. Remove those, and time becomes merely a coordinate, not an experience. This might sound like philosophical wordplay, but it has physical consequences. If time emerges from quantum entanglement, as some physicists propose, then observers only exist when there's sufficient entanglement. At heat death, entanglement is minimal. No observers. And without observers, the question, does time flow, becomes meaningless. There's no one to experience it flowing. Could time restart? In the context of cyclic cosmologies like Penrose's CCC, time doesn't restart so much as continue through the transition. The conformal boundary between aeons isn't a moment where time stops and then starts again, but a mathematical identification and where the far future of one aeon is smoothly connected to the distant past of the next time, flows continuously, but the clock resets. The thermodynamic arrow re-establishes itself with new low entropy. In other cyclic models, like the ekpyrotic universe or loop quantum cosmology, there might be a bounce where contraction becomes expansion. What happens to time at the bounce? Does it pause, reverse, continue forward? The mathematics suggests it continues forward. Even at the bounce, causality flows in one direction. The state just before the bounce influences the state just after. The arrow might wobble, might behave strangely in the extreme quantum gravity regime near the bounce, but it doesn't reverse. Time keeps flowing toward higher entropy, which in these models means through the bounce and into the next expansion. The anthropic point is worth remembering. Observers only exist when there's a thermodynamic arrow. We require entropy gradients, energy flowing from sources to sinks, enabling the complex chemistry and information processing that constitutes life and consciousness. Without the arrow, we don't exist to wonder about it. This means we necessarily experience time flowing in a particular direction, not because that's the only possibility, but because only that possibility is compatible with our existence. The question, what is time like when it doesn't flow, can't be answered by beings whose existence requires time to flow. At heat death, with no thermodynamic arrow, there are no observers. Time becomes something that exists in principle, but isn't experienced by anyone, like asking what colour is to a blind person, or what sound is to someone deaf from birth. The concept exists, the physics is there, but the subjective experience is absent. In this sense, time at heat death might continue but be meaningless. The universe exists, space expands, quantum fields fluctuate, but no one is there to divide these events into past, present, and future. No one to experience the flow. Time becomes an abstract parameter rather than a lived reality. And if something then happens, a quantum fluctuation creating new structure, vacuum decay resetting the physics, a new cycle beginning, the thermodynamic arrow re-establishes itself. Entropy begins increasing again from whatever the new low entropy starting point is. Time acquires meaning again. The flow resumes. Time might be less like a river that flows whether we're watching or not, and more like a story that only exists when it's being told. The universe at heat death is between stories, the old story finished, the new story not yet begun. The book is closed but not discarded. The play has ended, but the stage remains. Whether time is fundamental or emergent, whether it flows continuously or can restart, whether it's absolute or relative, these questions touch the deepest mysteries of existence. We experience time so intimately, so immediately, that it's hard to step back and see it as something that might be contingent, emergent, dependent on conditions that won't always hold. But physics suggests exactly that. Time's arrow emerges from entropy. Its flow requires change. Its meaning depends on observers. At heat death, some or all of these requirements might not be met. Time might continue mathematically while losing its physical significance. Or perhaps in the next quantum fluctuation, the next phase transition, the next cycle of whatever process follows our heat death, time will restart. Not literally starting over, but reacquiring the properties, directionality, irreversibility, meaningfulness that we associate with time as we know it. The heat death might be the universe holding its breath, the pause between inhale and exhale, the silence between movements in a symphony. Not the absence of time, but its suspension, waiting for something to give it meaning again. And when that something happens, whatever it might be, time doesn't so much restart as resume. The story continues. The play's next act begins, and observers in that distant future, if such exist, will experience time flowing forward just as we do, unaware that there was ever a pause, a silence, an era when time existed but had no one to mark its passage. We've journeyed far to the heat death of the universe and beyond, exploring theories of what might come after. We've contemplated vacuum decay rewriting the laws of physics, baby universes budding from quantum foam, eternal inflation creating infinite cosmos, and cyclic cosmologies where endings become beginnings. These timescales are so vast they make human history vanish into a rounding error. So why does it matter? What does the far future tell us about the present? Let's start with where we are in cosmic time. The universe is 13.8 billion years old. Star formation will continue for perhaps another 100 trillion years. The stelliferous era, the age when stars shine, will last about 10,000 times longer than the current age of the universe, and then the dark era, stretching for timescales measured in 10 to the power of 100 years or more. We exist in cosmic spring. The universe is young, active, full of light and energy. Stars are being born, planets are forming, complex chemistry is possible. Life flourishes, consciousness has emerged, at least here, possibly elsewhere. But this is brief. Cosmically speaking, absurdly brief. If the universe's history from Big Bang to heat death were compressed into a single year, the stelliferous era would last about 2 weeks. Human civilization would occupy less than a millisecond. Individual human lives wouldn't even register. This perspective is simultaneously humbling and profound. Humbling because it places us in an infinitesimally small window of cosmic time, but profound because we happen to exist during the only era when observers are possible. Heat death doesn't support complexity. The dark era can't sustain life. We exist when and where we do, because only this narrow window, this cosmic spring, allows creatures like us. This is anthropic reasoning. Not that we're special, but that observers necessarily find themselves in observer-permitting conditions. We can't observe the dark era because observation requires energy gradients, structure, complexity, all of which the dark era lacks. The fact that we exist now tells us that now is special in at least one way. It permits existence. But our specialness is temporal, not fundamental. We're not witnessing anything unique. Stars have been forming and dying for billions of years before us. They'll continue for trillions of years after. We just happen to be here during the long middle period when such things occur. The theories we've explored, vacuum decay, baby universes, eternal inflation, cyclic cosmologies, all suggest that heat death might not be final. Our ending might be a transition, a threshold, a pause before something else begins. If that's true, what does it mean for how we live our brief lives? First, it provides perspective. The universe is not rushing toward an ending. Even heat death, if it comes, arrives after timescales that dwarf current cosmic age, and it might not even be final. The heat death of our pocket universe would be just one event among infinite events. If eternal inflation is correct, our ending becomes less significant, not meaningless, but local. One note in an infinite symphony. Second, it suggests the universe is more interesting than we thought. Not just a one-time event running down towards silence, but possibly cyclic, or eternal, or fertile with possibility. Reality might be stranger, richer, more creative than the simple story of Big Bang to heat death suggests. Third, and this feels important, it means endings aren't absolute. Every ending we've explored contains the seeds of something new. Vacuum decay transforms physics, baby universes bud from black holes. Eternal inflation continues forever. Cyclic cosmologies loop back. Even in scenarios where our particular universe ends absolutely, something else begins elsewhere or elsewhen. This doesn't make our ending less real. We will still end. Our sun will die. Our galaxy will go dark. The structures we build will dissolve, but it places that ending in a context where transformation, rather than annihilation, is the pattern. Does this give life meaning? That depends on what you mean by meaning. If meaning requires permanence, that our works must last forever, that we must leave an eternal legacy, then no physical cosmology offers comfort. Even cyclic universes don't preserve individual structures or memories. Everything local eventually dissolves, regardless of what comes after globally. But if meaning comes from experience, connection, understanding, from the quality of existence rather than its duration, then cosmology changes nothing. The fact that the universe might continue in some form after our heat death doesn't make our experience more or less meaningful. We still love, create, suffer wonder. The distant future's existence doesn't diminish the present's reality. There's something to be said for the Buddhist perspective here. The fact of impermanence, that all conditioned things are temporary, doesn't make them meaningless. Indeed, their temporariness might be what gives them poignancy. The cherry blossom is beautiful partly because it falls. The moment is precious partly because it passes. Our cosmic situation is similar. We exist during a narrow window of cosmic time in a narrow range of cosmic space, under particular physical laws that permit complexity. This temporariness doesn't diminish the experience. If anything, it enhances it. We're witnessing something rare, the universe at a stage when light exists, when structure forms, when consciousness can emerge and contemplate its own existence. The fact that we understand this, that we can calculate heat death, explore what comes after, contemplate our cosmic context, is itself remarkable. We're the universe's way of knowing itself, to borrow Carl Sagan's phrase. For a brief period, in a tiny corner of space, matter has organized itself into patterns complex enough to understand the cosmos. That understanding doesn't need to be eternal to be valuable. Consider the physical constants that make our existence possible. The electron mass, the strength of gravity, the cosmological constant, all appear fine-tuned for complexity. Change them slightly, and atoms don't form, or stars don't shine, or galaxies don't coalesce. Why are they just right? If eternal inflation is correct, the anthropic answer becomes compelling. With infinite universes exploring all possible values, some will have the right combination. We find ourselves in one of those because only those allow observers. It's selection bias on a cosmic scale, but it explains the apparent fine-tuning without requiring design or luck. This shifts the question from why are the constants right to why does anything exist at all? And that question remains open. Cosmology or no cosmology? The multiverse explains our particular constants, but not why there's a multiverse. Cyclic cosmologies push the beginning infinitely into the past, but don't eliminate the mystery of existence. Perhaps some questions can't be answered by physics, not because physics is limited, but because the questions themselves live outside physics' domain. Why anything exists rather than nothing is a philosophical question, possibly a meaningless one. Physics describes how things are, not why there's something rather than nothing for those descriptions to apply to. But we can appreciate what physics does tell us. The universe is vast, possibly infinite. Time is long, possibly eternal. Our moment is brief but real. Our experience is temporary but genuine. And the cosmos might be stranger and richer than we imagine, fertile with possibility, eternal in some sense, transforming rather than merely ending. There's something comforting about eternal inflation or cyclic cosmologies, not because they promise our personal continuation, they don't, but because they suggest the universe is alive with possibility, not just running down towards silence. Somewhere, somehow, something continues. The cosmic story doesn't end, even if our chapter does. And there's something democratizing about these ideas. We're not at the center of space. Copernicus taught us that. We're not at the center of time. We exist 13.8 billion years into an enormously longer story. We're not unique physically. The same laws operate everywhere. And if the multiverse is real, we're not even unique cosmically. Our universe is one of infinitely many. Each discovery has been humbling. Each has pushed us further from centrality. And yet we remain able to understand our place in this vast structure. The fact that we're peripheral doesn't mean we're irrelevant. It means we're part of something grander than we imagined. The practical implications are subtle. Knowing about heat death or cyclic cosmologies doesn't change how you should live today, but it might shift perspective. The petty concerns that loom large in daily life shrink when viewed against deep time. Not to insignificance, your life matters, your relationships matter, your choices matter, but into context. At the same time, the fact that everything is temporary on cosmic scales doesn't mean nothing matters on human scales. This moment is the only one you have. These relationships are the only ones you'll experience. This life is the only one you're certain of. Cosmic perspective doesn't diminish human experience. It frames it. There's an old thought experiment. If you knew the world would end tomorrow, would you plant a tree today? The answer says something about where you find meaning. If meaning comes only from lasting consequences, you wouldn't plant the tree. If it comes from the act itself, from engagement with life, from doing what feels right regardless of outcomes, you plant the tree. Cosmology tells us the universe will end, though not tomorrow. Do we still build, create, love, wonder? If our answer is yes, and for most of us it is, then we've answered the question of whether cosmic endings diminish present meaning. They don't. Meaning comes from engagement, not from permanence. We are, in a very literal sense, made of stars. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all forged in stellar cores, scattered by supernovae, gathered into planets, incorporated into life. We're the universe's way of knowing itself, temporarily, locally, but genuinely. And for this brief cosmic moment, we can understand our situation. We can calculate how long stars will shine. We can predict heat death. We can theorize about what comes after. This understanding is a gift. We're the first generation of humans to see the full arc of cosmic history, from Big Bang to far future. Previous generations wondered about origins and endings but couldn't know. Now we know, or at least we have good theories based on solid evidence. The privilege of this knowledge is rare in cosmic time. For most of the universe's future, there will be no one to possess it. So, what does it mean for us? These theories of what comes after the end. It means we exist in a universe richer than we might have guessed. It means endings might be transitions rather than finalities. It means the cosmic story continues, even if our chapter concludes. It means we're part of something vast, strange, and beautiful. And it means this moment, now, while stars shine and galaxies swirl and consciousness exists to appreciate it all, is precious. Not because it lasts forever, because it doesn't, because it's rare, because we're here to witness it. The universe is patient, consciousness is brief, wonder is timeless, and the fact that we can stand in this cosmic spring, understanding both where we came from and where we're going, knowing our moment is temporary but real, that's enough. That's everything. That's the gift of existence in a universe vast enough to contain heat death and strange enough to possibly transcend it. We've reached the end of our trilogy through deep time, from following a single black hole through 10 to the power of 69 years of existence, through contemplating the profound silence of the dark era, to exploring theories of what might lie beyond heat death. We've journeyed as far as physics and mathematics can take us, and perhaps a bit further into the territory where science meets carefully disciplined speculation. What have we discovered? That heat death might not be final, that vacuum decay could rewrite reality's rules, that quantum tunneling might birth baby universes from apparent emptiness, that eternal inflation might create infinite cosmos, making our ending just one local event in an eternal process, that cyclic cosmologies might loop time itself, turning our heat death into someone else's Big Bang. These aren't fantasies. They're serious proposals from accomplished physicists, grounded in quantum mechanics and general relativity, attempting to answer questions humans have always asked in new ways. What comes after the end? Can something arise from nothing? Is the universe unique or one of many? Does time have a beginning? We don't know which theories, if any, are correct. We might never know. Some live beyond the reach of testing, at least with current or foreseeable technology. But the exploration matters. These questions reveal the boundaries of knowledge, show us the frontier between what we understand and what we wonder about. And they change how we think about our moment. By understanding the universe's possible futures, we better appreciate our present. By grasping deep time, we see our moment's rarity. By contemplating heat death and what might follow, we recognize how special this cosmic spring is, this narrow window when stars shine, complexity flourishes, and consciousness can emerge to contemplate it all. We are the universe's way of knowing itself, briefly, locally, imperfectly, but genuinely. We exist during the only era when observers are possible, made from dead stars, animated by energy flowing from sun to earth, capable of understanding our cosmic context. That remains extraordinary, regardless of what comes after. Thank you for taking this journey through deep time with me, from stellar birth to stellar death, from black hole formation to black hole evaporation, from the stelliferous era's noise to the dark era's silence, from heat death's apparent finality to the possibilities beyond. We've travelled farther than light could go in the universe's current age, contemplating timescales that make billions of years seem brief. Now we return to our human scale, to our brief lives, to our present moment. But we return changed, carrying this perspective, the long view, cosmic humility, and perhaps a deeper appreciation for existence itself. The stars still shine above, the universe still expands, entropy still increases, and we still wonder which might be the most remarkable fact of all. Somewhere, 10 to the power of 100 years from now, in a universe cooled to near absolute zero, a quantum fluctuation might occur. A bubble of new physics might nucleate time, might begin again. The cycle might continue. Or maybe not. Maybe the silence is eternal, the heat death truly final, the ending absolute. Either way, now, in this brief cosmic spring, we are here, conscious, understanding, appreciating, creating meaning from physical processes, beauty from mathematical structures, wonder from entropy's patient work. That's enough. That's everything. That's the gift of existence in a universe vast enough to contain heat death, and strange enough that we can contemplate what might lie beyond. Sleep well, knowing you've glimpsed the longest view. Dream of deep time, of possibilities beyond ending, of universes budding from the void, and wake grateful for your narrow window of light in the cosmic vastness, this improbable moment when consciousness exists to wonder about it all. The universe is patient. Consciousness is brief. Wonder is eternal. What comes after the universe ends? Perhaps another universe. Perhaps nothing. But here, now, something exists. And that something includes you, wondering about it all, which might be the most extraordinary fact in all of cosmology. This is the Sleepy Astronomer thanking you for wondering with me and wishing you a very good night.